Hello, today we're looking at small angle approximations, which is another nice thing that we can do in radians, which we couldn't do before in degrees. What it allows us to do is, rather than fully calculating a question, we can use some proven identities and substitute those in instead. And what it can kind of help us do is it helps us work out some trig questions without actually having to use a calculator. Okay, now if you want to test how good your calculator actually is, you can do something called the sign test. Okay, now this only works in radians, and what you want to do first of all is start off by just typing in sine 1 and press equals. Okay, now what the sign test does is it'll work out how good your calculator is to so many decimal places. Okay, so your calculator is probably a decent calculator. It's only going to be good enough to a certain degree of accuracy. Most kind of basic calculators may go to only a couple of decimal places. These Casio ones we're about to put to the test. What we're trying to do is we're going to make this 1 smaller by a factor of 10 every time. And we're going to try and see when the angle up here is the same as the answer. Okay, it doesn't actually make any major difference here, but it just kind of shows how good your calculator is. So if I now change this to 0.1, you can see that my answer is almost 0.1, but it's not exactly 0.1 yet. Okay, if I now make it 0.01, again, we're very, very close to 0.01 as an answer, but it's not saying 0.01 yet. Let's try 3 decimal places. Again, it's still trying, it's working it out. It's slightly different. There's some variation between the angle and the answer. Let's put another 0 in. Again, it's still not there, but very, very close. And at that moment there, that's when your calculator's kind of giving up. It's just saying, yeah, whatever, it's this thing here is just the same as what it is. Okay, so that's quite impressive for a calculator. So it's gone up to 5 decimal places. My guess would be maybe a basic Casio one might only go to about 3 decimal places, maybe 4. To be honest, in the long run, it doesn't make much difference to what our final answers are going to be. It just kind of shows you though how good your calculator is and kind of how much processing power it's kind of got behind it. Okay. If you've got the same calculator as me, there's no point trying it. But if you've got a different calculator, it might be worth just trying to type it in sometime. Now this here then, this is our first small angle approximation. It says sine of a very small answer, sine of a very small angle just gets you that angle. There seems to be no difference between the angle we've put in and what happens when we do sine of it. Okay, so that, I'll write this on the board, that here is our first approximation. If we put an angle in and it's very, very small, your calculator is just going to say, it's whatever the answer is in the first place. Okay, if we did it for tan, we could do the same idea. I know it's 5 decimal places now. Oh, look at that, it's the same idea again. So we've put in tan of an angle, and the calculator says, oh, it's just the same as the angle that you've put in. So the tan small angle approximation is also just the same as the previous one. Now the cos one, you probably won't be able to guess what it is. If I start with 1, we get 0.54. We can't really tell what's going on there. If I make it smaller by a factor of 10, it's gone from 0.1 now to 0.995. If I make it smaller again, and as you can see now, we're getting closer and closer to 1, and hopefully at some point we probably will get 1. And I'm guessing it's the 5 decimal places again. Okay, now there's no way you'd be able to guess what's happening here, so I'm just going to have to come out and tell you what it is. The cos small angle approximation is this. If you put an angle in and it's small, the answer is pretty much going to be 1 minus your angle squared over 2. Okay, so they are the 3 small angle approximations, and the very, very, very good news is you do not need to remember any of these because they will be given in your formula booklet. However, on today's sheet, they are going to be on the top of the page, and I'm going to keep them on screen there so that we can use them to help us work out some answers. Okay, so in a slightly different order, but they're exactly the same as what I've just kind of shown you on a calculator. So sine is just the same as the angle. Cos is a bit more of a weird one. It's 1 minus the angle squared over 2. Tan is going to be the same as the angle. Now the reason this kind of works is if I show you the 3 graphs, which again is on the sheet anyway, so you can have a look at it on your sheet rather than on screen, is if we were to plot, if we look at the first graph in particular, the sine graph against y equals just theta, there's quite a big section there where the red line and the black line look pretty much identical. Okay, so for them small values of theta, the red line and the black line are going to be pretty much the same number, which is why that small angle approximation works. It's the same with the tan one, the one on the far right. There's going to be a good section there where there's not going to be much, if any, difference between the red line and the black line. And then for the cos graph in the middle, it does look like it's less of a similarity there, but it's still right at the peak of both graphs. They look very, very similar, which is why we can apply these approximations to help us, like I say, work out some trig without technically having to use a calculator. Okay, so now let's have a look then at some of the questions that we need to be doing. Here's the first one. Okay, it says, when theta is small and measured in radians, find approximate values for each of these expressions. Now, one thing I did fail to say was this thing here, which is currently on screen. It says, as a general rule, if theta is small, then any multiple of theta is also small. So if we had sine of 3 theta, that's just going to become 3 theta. If we had tan of 2 theta, that just becomes tan 2 theta. And for cos, if we have cos of 4 theta, then this theta here has to now become a 4 theta in brackets before we square it and then divide it by 2. Okay, and as you can see from this question already, we're going to have to kind of use that idea to work out some approximations. So the first one then says we want get an approximate value for sine 2 theta plus tan theta over 2 theta. So we know then that sine 2 theta, an approximate answer for that, if this is small, is just going to be 2 theta. For tan, if we've got tan of theta and that's small, that's just going to be theta. So that means sine 2 theta plus tan theta over 2 thetas is now going to become 2 theta plus theta over 2 theta. This is 3 thetas over 2 thetas, so an approximate answer is going to be 3 over 2. The thetas would cancel out. We've got 3 in the top, 2 at the bottom. And if we wanted to, we could maybe check that on a calculator if we put a small number in. Get a fraction. Sine 2 of the small angles plus tan of the small angle over 2 of those angles equals 3 over 2. Okay, so our approximations definitely do work, and you can do that for pretty much most questions that we're going to be looking at here. I'm not going to do it for every question, but you can check to see if it works. Okay. Second question says, what's happened there? That's come back on screen. I didn't want that one. I wanted it to go. Is the second one. Here it comes. So it says cos of 4 theta minus 1 over theta sine 2 theta. So let's do it the same way. We know cos 4 theta is approximately 1 minus 4 theta squared over 2. Let's try and simplify this here. Well, 4 theta squared would be 16 theta squared. Divided by 2 is 8 theta squareds. So that is going to be 1 minus 8 theta squared. The other trig part we've got is at the bottom. That looks very similar to one we've just previously done. So now then, when we substitute that in, we get 1 minus 8 theta squared minus 1 over theta times by 2 theta. So we've got 1 minus 1, that's gone. At the top we're just going to have a minus 8 theta squared. At the bottom we have 2 theta squareds. The theta squareds would cancel out. Minus 8 divided by 2 is minus 4. So my approximate value for this one would be minus 4. Okay, question 2 looks a bit more wordy. It says, show that when theta is small and measured in radians, sine 5 theta plus tan 2 theta minus cos 2 theta is pretty much the same as 2 theta squareds plus 7 theta minus 1. Okay, it's just written in more words, but it's exactly the same as question. So we've got sine 5 thetas, so that's going to be 5 theta. We've got tan 2 theta, that's going to be 2 theta. And then we've got cos 2 theta, which is going to be the same as 1 minus 2 thetas squared over 2. Well, 2 theta squared is 4 theta squared, divided by 2 means what we're going to have is 1 minus 2 theta squared. And now if we plug it in to that line there, the first thing was we wanted sine of 5 theta. Well, that is sine 5 theta plus tan of 2 theta, which is this thing, so that's plus 2 more thetas, minus cos 2 theta. We need to take this away, so it's going to be minus 1, and minus this minus makes it into a plus. And if we simplify this, we're going to get 2 theta squared plus 7 thetas minus 1, which is what the question wanted us to do. Part B says, hence state an approximate value for the original question. Well, the original question is the same as this. It's only the same as this when theta is a very, very small number. So a very, very small number squared, we can pretty much just ignore. 7 lots of a very, very small number, we can just ignore. So it's just going to be this minus 1. An approximate answer for that would be minus 1. It's a bit like when we did the differentiation by first principles. We kind of said when things tend to 0. That's similar to what's happening here. This is a small number, this is a small number. So if we have some small numbers, they're going to be just eliminated because they're just too small and insignificant. So we're just going to call it minus 1. And in the last example, it says when theta is small, show that 32 cos 5 thetas plus 203 tan 10 thetas equals 182 can be written as 40 theta squared minus 203 thetas plus 15 equals 0. Okay. And even again, it might look nasty, but the steps are pretty much going to be everything we've just done. So I can see that we have a cos 5 theta. That's going to be pretty much the same as 1 minus 5 thetas squared over 2, which is the same as 1 minus 25 theta squared over 2. We've got a tan of 10 theta, which I'm just going to call 10 theta. And now we can start substituting those two bits into the equation we've got. We want 32 cos 5 thetas, so we want 32 lots of 1 minus 25 theta 2 squared, over 2, plus 203 lots of tan 10 theta equals 182. Right, we need to multiply out these brackets. 32 minus, well, 25 times 32 divided by 2 is pretty much the same as 25 times by 16. So that's going to get us minus 400 theta squared. You can use a calculator if you don't believe me. Plus 203 times by 10 thetas is 2030 thetas equals 182. Let's take everything across to the right hand side, so we get positive theta squareds. So that's going to be nothing left over here equals 400 theta squared minus 2030 thetas, and then it'll be 182 minus 32, so that's going to be a plus 150, which now looks very similar to what we need, except for all we need to do now is divide everything by 10. If we divide everything by 10, we get equals 40 theta squared minus 203 thetas plus 15, which is what the question wanted us to do. Now for part B it says, hence find one approximate solution for the very first line. So we know it's the same as this green line at the end. So if we can solve the green one, we can solve the original. Well, that's a quadratic, so let's plug it straight into our calculators. Polynomial. We've got 40 theta squareds minus 203 thetas plus 15 equals. Now we do get two answers, but the question does say find one approximate solution. So if I look at what my two answers are, we've got 5 and we've got 0.075. And we now need to kind of say which answer we're going to pick and why we're going to pick that answer. And we're going to pick the 0.075 because this only works if theta is a small number. Okay? And what we're going to say is 5 in this case is not small enough. We really want it to be like a 0.0 something number, which is what happens for this answer here. So the one approximate solution is going to be 0.075. We should probably write out both answers and then maybe quickly explain why we don't want 5, and it's just going to say 5 is not small enough. Okay, so that's all the questions, or the examples rather, on today's worksheet. If we look at what we needed to do, so that's the sheet that we should have just hopefully filled in. I think I've gone through everything on the front and the back. We've done all those examples, that's good. So on to the questions then. It is single-sided, that's always good news. So questions 1 and 2 do not look too bad at all. Question 2 is even sure that's, so that should help us out. Question 3 is just kind of, again, it's like another proof, just to kind of show you how good things are. So it says find cos of this and cos of a second one, and then it says calculate the percentage errors after you've done the approximations, and it says explain the difference. So what you should probably find is that the smaller value, I think it says 0.244, the percentage error for that one should be smaller than the other one because it's a smaller number. Okay, that's pretty much what you have to kind of write there for 3D. 4 does not look like it is too bad at all. And I don't think question 5 is too bad. So give those questions a try. If you do get stuck, let me know. I have been away from my computer for the last day. I know there was a few messages on Microsoft Teams rather, that I will try and answer on Thursday or in Thursday's lesson. But if you are stuck, please let me know. And that is it for today. So we have done some small angle approximations. Like I said, try and remember them. You don't need to memorize them. They will be given in the formula booklet. Give the questions a try, and if you get stuck, let me know. I will see you all next Tuesday for our double maths lesson.